Welcome to Circuit Chats, your go to podcast for breaking down the world of electronics, one topic at a time. I'm your host, and today we're diving into the fascinating world of semiconductors, the building blocks of modern technology. So let's talk electronics. Before we get hands on with gadgets and circuits, it all starts with the basics. Today's agenda comes straight from Chapter 1 and covers five key concepts: atomic structure, valence electrons and ionization, types of materials, semiconductors, both N and P type, and finally the magic behind it all, the PN junction. Hey everyone, welcome back to Circuit Chats, the podcast that makes electronics simple, snappy, and totally electrifying. Today we're taking it all the way down to the atom. That's right, atomic structure, the start of everything. So to understand electronics, we have to start with atoms. And no, not atoms like in sci-fi laser cannon. I'm talking about real atoms, the tiniest bits of stuff that still act like the element that they came from. So whether it's copper, silicon, or gold, every material begins with these little guys. So let's go ahead and look inside the atom, right? Go ahead and imagine that the atom, like a tiny little solar system, it's at the center, and you've got this nucleus at the center, and that is dense, and it's packed with protons and neutrons. And protons are those little things that have a positive charge, and neutrons, these are like the chill roommates, have no charge, they're just going to hang out. So orbiting around that nucleus, like planets around the sun, are the electrons. And these little particles have a negative charge, and they're always on the move. Now we see here that we're looking at the Bohr's model of the atomic structure. So you might have seen diagrams where electrons are swirling in loops around the nucleus. That's what we call the Bohr's model. And it's not exactly how atoms work in real life, but it helps us picture what's going on, especially when we talk about how electrons jump around in semiconductors. And so, why do we care about electrons? Well, because in electronics, electrons equal action, right? They carry the current, they flip your bits, they power your screen. They basically do all the work in a circuit. So, the way they move or don't move inside a material decides whether that material is a conductor, an insulator, or a semiconductor. Let's break down the building blocks of electronics one atom at a time. So, today's episode is all about the powerhouse of the center of the atom, and that's the nucleus. So, picture an atom again, tiny and visible to the eye, but packed with structure. And at its core is the nucleus. This isn't just some empty center, it's where the massive stuff hangs out. The nucleus is made up of two particles, the protons, which have a positive electric charge, and then the neutrons with no charge at all. They're just kind of hanging around there. And together they give the atom most of its mass. If the atom were a concert, the nucleus would be the stage, heavy, central, where all the power originates. Now, going back to Bohr's big idea, the Bohr's model, that classic diagram that you've seen in textbooks. So, in this model, electrons don't just float around randomly. They have definite orbits like planets circling a sun, and these orbits are called energy levels. They're they're like how atoms interact with electricity. So this matters because in electronics, understanding the nucleus helps us get why atoms are stable, why electrons can jump from orbit to orbit when they're energized, and that jump is where current flow and energy transfer begins, and that's the whole game in electronics. Okay. So with that said, we're going to go ahead and take a look at those electrons that are sitting in those orbits, and we're going to talk about something called valence electrons, which are the outermost rebels, right, that decide if something conducts electricity or not, or if they're going to resist. We've talked about atoms, the nucleus, and those speedy little electrons. Now let's connect the dots between electrons, atomic number, and why every element is basically its own unique flavor of matter. So let's talk electrons and identity, right? So electrons are just tiny particles flying around. They actually define how an atom behaves. So whether an atom forms a bond, whether it jumps into a chemical reaction or helps current flow, all of that depends on what the electrons are doing. So think of them as the personality of the atom. And then next, we're going to jump onto the periodic table on the next slide. But what is a periodic table? Right? So every element on that periodic table has a special ID, and we call that the atomic number. And that number tells you how many protons are in the nucleus and in a balanced atom, right? It also tells you how many electrons are orbiting around it. So if you look at hydrogen, for example, it has one proton, one electron. If you were to look at oxygen, it has 8 and 8, right? Silicon, the rock star semiconductors, that has 14 protons and 14 electrons. And so that means that we have a balanced charge. So the atom basically is neutral. When the number of positive protons matches the number of negative electrons, the atom, we call that electrically neutral. It doesn't have a charge. And that balance is what makes the atom stable, at least until it starts reacting or conducting. And this matters in electronics because when atoms gain or lose electrons, especially the ones on the outside, which is the valence electrons, they can become charged and conduct electricity, and that's exactly what semiconductors are designed to control. Okay, now we're getting up close with something that hangs in every science classroom, and that's the periodic table. But this time we're not going to try to memorize it. We're going to look at decoding it. So, what is a periodic table? The periodic table is the ultimate cheat sheet for the universe. It's a map of all the known elements. It's arranged, but not randomly. It's arranged by atomic number, by the structure, and the behavior. Let's go ahead and put a spotlight on the atomic number first, right? So remember we talked about that the atomic number tells you how many protons, and in a balanced atom, how many electrons are given for that particular element. It's how we tell one element from another. So um, let's focus in on silicon, which is element number 14. It's right in the middle of the table between the metals and the nonmetals. It's a little sweet spot called the metalloids, right? And that's not an accident. So these are the elements that can act both like conductors and insulators, and that's what makes silicon so perfect for electronics. But who else is on the team of the semiconductors? If you look at silicon's neighbors, like germanium, designated by the symbol capital G, little e, and arsenic, capital A, little s. These also play a big role in semiconductor design, but silicon is the most abundant. It's the easiest to work with. So for right now, let's just stick with semiconductor silicon material for transistors and chips. Now you can also see there's some color coding here to the families on the periodic table. The periodic table groups elements by, in this case, color and columns, and we call those families. So elements in the same column usually have this, they behave the same way. That's why, like, if you look at sodium and potassium, both of them in that first group, they react explosively with water. And why the noble gases, which are on the far right, they barely react at all. So next time you look at the periodic table, don't just see a bunch of boxes and numbers. See the patterns, see the predictability. And again, since you're in electronics, definitely keep your eye on the middle zone where the semiconductors live. You're tuned in to Circuit Chats, where atoms get animated and electrons take the spotlight. Today we're going orbital, literally, because we're talking about electrons and shells. Inside every atom, electrons don't just zip around randomly, they live in specific energy levels or shells that orbit the nucleus. So think of it like a layered onion, or better yet, like seating in a concert hall. And the seats closest to the stage are the lowest energy, the nosebleeds are the higher energy, right? So let's talk about silicon, which has an atomic number 14. That means it has 14 electrons arranged in three shells, where shell 1 holds 2 electrons, shell number 2 holds 8 electrons, and shell number 3 holds those last 4 electrons. The outermost shell is the real VIP section here. We call those the valence electrons, and they decide how atoms interact and whether a material conducts electricity. Now, there's a rule for shells. It's a handy little formula that'll tell me the maximum amount of electrons in the shell, and that formula is 2 times n squared, where n is going to be the number of the shell. So in other words, for shell number 1, it's 2 times 1 squared, because we're in shell 1. That's going to give me 2 electrons. That means that's all I can hold. Shell number 2, 2 times 2 squared, that gives me 8 electrons. Shell number 3, 2 times 3 squared, That's going to give me 18 max. But remember, silicon just uses 4, right? So why is this important for electronics? Well, because in electronics in the outer shells, especially when they're only partially filled, they're more likely to move around, and that's what lets silicon behave like a semiconductor. It's not too clingy with the electrons, but also not too loose either, so it's just right. So let's go ahead and quickly recap what we talked about here. Electrons close to the nucleus equals less energy. Electrons that are further away from the nucleus, they have more energy. Shells are energy zones. And the valence shell, that's the one we'll keep coming back to, which is the outer shell. We've built up atoms, shells, and energy levels, but now we're ready to meet the VIPs of electrical behavior. That is the valence electrons. So valence electrons are those outer rebels. Um, they live in the outermost shell of the atom, the farthest away from the nucleus, and that means that they feel the least pull from the positively charged center, and they've got a higher energy and more freedom to kind of move around. And why do we care about this? Well, because these are the electrons that actually do things. They're the ones that form chemical bonds, they start reactions, and most importantly for us, they carry electrical current. Now, remember the relationship of distance equals less control. So the farther away an electron is from the nucleus, the weaker the attraction pulling it in. And it's kind of like holding a dog on a long leash. The longer the leash, the less control you have. And with valence electrons, the leash is pretty long. So let's go ahead and go further into valence electrons and how it relates to electronics. So in materials like silicon, valence electrons can break free and move under the right conditions, like when energy is added. That's what makes semiconductors so powerful. They don't always conduct electricity like metals, but they can, and they can when we want them to, which is more important. So again, let's do a quick review. Valence electrons live in the outer shell. They're less tightly bound to the nucleus. They're responsible for chemical bonding and electrical properties, and they're the reason we can build microchips, diodes, and transistors. Electrons aren't just particles, they're heroes of our story. So today we're talking about something that gets electrons all fired up, literally, right? It's time to talk about ionization. So what is ionization? So when an atom soaks up energy from heat, light, or electricity, its electrons start to get excited, not emotionally, of course, but energetically. And when these energized electrons, especially the valence electrons on the outermost shell, well, they can absorb enough energy to break free from the atom completely. And when that happens, boom, we have ionization, right? So this is how it works. A valence electron absorbs a specific amount of energy called ionization energy, and then once it reaches that threshold, the electron escapes the pull of the nucleus and it becomes a free electron and it's able to move through space or through some material. And this matters in electronics because free electrons are exactly what we need in circuits. So in semiconductors, we add energy like voltage to control when and how electrons become free. So we can switch currents on and off with precision in these materials. And that's kind of the entire principle behind transistors. So what happens to the atom, right? So when the electron leaves, the atom is left with one fewer negative charge, and that makes it a positive ion, meaning it's positively charged because it's less negative charge, right? Ionization isn't just about the electron though. It's also it also changes the atom's identity. So a recap from this slide, that's all we got to cover here, is ionization happens when a valence electron gains enough energy to escape. This creates a free electron and a positive ion, and it's the key to how we manipulate current in semiconductors. So we explored how energy can knock electrons loose from their atoms. Today we're putting that concept into motion with a picture that you can almost see through your headphones. So picture this, you've got an atom sitting peacefully surrounded by its electrons in a neat orbit, and then bam, a wave of energy hits it. And again, it could be heat, it could be light, it could be electricity. Either way, energy is supplied, and that green squiggly line that you see there on the slide, that's the energy being supplied, right? Pumping power into the atom. It targets those outermost valence electrons. the ones already hanging out by a thread, but they're just barely hanging on, and then the escape, right? When an electron absorbs the energy and takes off like a rocket, it escapes the atom's pull, it becomes a free electron, and just like that, the atom is no longer balanced. It's now a positive ion. And this is the spark of current. Free electrons are the real movers in an electric circuit. And in semiconductors, we can control when ionization happens, which that allows us to be able to switch currents on and off when we need to or we want to. And there, that is the basis for digital logic. And why does this matter? Well, this diagram isn't just a picture. It's the story of how we go from stable atoms to a world where electricity flows, and it's how your phone charges, your lights turn on, and how your computer actually runs. Right? So, with that said, let's go ahead and move on to the next topic. All right. So, if you've been following along, you know that electrons can move, but whether they're allowed to move depends on the material. And we're going to finally be breaking down the three big categories of materials, which are conductors, insulators, and semiconductors. And let's talk about defining them. So conductors, these are materials like copper, silver, or gold, where electrons move around fairly easy. Um, there's no gatekeeping here. Their valence electrons are very loosely held, so electricity flows like water going down a slide, right? Then on the other spectrum, excuse me, we have the insulators. And these are things like rubber, glass, plastic, where their electrons are locked in very, very tight. Valence shells are full and they're stable, so electricity can't flow very easily, if at all, in insulators. And now you have the in-betweeners, right? The semiconductors. So these are the stars of the electronic world. Um, so within semiconductors, electrons, they're not too free, they're not too rigid, they're kind of just in the right place. Silicon, again, being our classic example under normal conditions, is not very conductive. But if you tweak it, say by adding energy or a little impurity, it can switch on and conduct very easily at our control. All right, so let's talk about the two concepts here: intrinsic and extrinsic. You see on the flow chart there. That means that semiconductors come in two flavors, right? Intrinsic means it's pure, so 100% clean silicon. It conducts a bit, but not much. Extrinsic means we've added something to boost conductivity, and we call the process of adding this something, this impurity, we call it doping, right? So we have two types now at the very end, two types of doping. One is called N-type, and the other one's called P-type, right? So this is where things get interesting. Within N-type semiconductors, they're doped with atoms that bring extra electrons. So now there's more negative charge carriers. But with P-type semiconductors, these are doped to create holes, which are spaces where an electron could go. So these act like positive charge carriers. When you put it all together, when you have N-type and P-type materials, we can build the basic building blocks of electronics, like diodes, transistors, and integrated circuits. And right here, I would like to at least recommend for you all to watch any documentary that talks about the discovery of semiconductors. Right? You're listening to Circuit Chats, where science meets the spark of technology. We're digging deeper into material, the stuff that decides whether electricity flows freely, whether it gets stuck, or walks a careful line in between. So let's go and talk about insulators, which are the blockers, right? Let's start with these blockers. These materials don't like to share their electrons. Their valence electrons are locked down tight, no jumping around, no current flow, and that's why we use them to protect circuits. So for an example, think of materials like rubber, plastic, glass, mica, quartz, right? These are the safety gear for the electrical world. On the other side, we have the enablers, which are the conductors, right? So conductors are the opposite of the insulators. Their electrons are loose, free to roam, and ready to carry current. And that's why we wire our homes and phones with copper, silver, gold, and aluminum, because these are like the superhighways for electricity. Now we have the in-betweeners, right? The semiconductors. They're in the middle, or they're the middle child. And these are special not just because they're the middle child, they're special because their ability to conduct electricity can be controlled. Right? They don't always conduct, but with a little help, like a little heat, light, or doping, they can be set up that way. And you're going to find semiconductors and elements like silicon, germanium, arsenic, boron, um, and in their pure forms, right? When they're in their pure form, they're called intrinsic semiconductors, right? So they're neither a great conductor nor a good insulator, but they're right for just a little bit of manipulation to get them going. And this matters because every device that you own now, from laptops to LED lights, it depends on the balance between these three types, right? Knowing how they work means knowing how to shape the flow of electricity. So that's it. We're going to dive a little deeper into intrinsic and extrinsic semiconductors and how we can just sprinkle a few atoms and that can totally change how the material behaves. Okay, now we're going to be talking about something that's invisible but incredibly powerful in electronics, and that's called the energy band gap. So, what's the energy band gap? Inside a solid, electrons aren't just spinning around, right? They occupy energy levels, and these levels form what we call bands. And there are two main bands that we care about, the valence band and the conduction band. The valence band is where electrons are still bound to the atom, and the conduction band, which is where electrons are free to move through the material and carry current. Now, let's talk about the gap between bands. Here's the thing, those two bands aren't right next to each other. There's a space between them, and that space is called the energy band gap, right? This gap represents the amount of energy an electron will need so that it can jump from the valence band to that conduction band. Think of it like a skateboarder needing just the right push to launch off a ramp and do a rampy dampy thing. Yeah, I don't know the lingo. So anyway, back to the electron. How does it work? So you supply enough energy, again, through heat, through light, or voltage, and an electron jumps that gap. Once in the conduction band, it's free to move around. It's a free electron. So it's ready to help out in the form of electrical current. And the size of the gap determines if a material is going to be a good conductor, an insulator, or a semiconductor. And this is why semiconductors rock, because semiconductors, like silicon, they have small band gaps and just enough to control electron movement with some precision. So we can open or close the gate using just a little bit of energy, which is how we build logic gates, switches for memory. So yeah, all that's based just on this particular concept. Let's go ahead and do a quick recap on this slide before we move on. Now we talked about the valence band. That's the where electrons are still bound to the atom. We got the conduction band. That's where electrons are free moving. We got the energy band gap. That's that leap between the valence and conduction band. And reminder that um, within semiconductors, that leap is very, it's just at the right spot. So it's not too easy. It's not too hard. Um, And so let's continue. Now that we talked about the energy band gap, which was that invisible space that electrons need to leap over so they can conduct electricity, we're going to be putting that idea on the screen with the energy band diagram. Right? So picture three materials side by side. Imagine three energy towers, one for an insulator, one for a semiconductor, and then one for a conductor. And each tower shows two levels. So the valence band at the bottom, where electrons normally just hang out, they chill. And then the conduction band at the very top, and that's where electrons get to party, they get to move freely. But let's go ahead and zoom into each one of those. Let's look at the insulator. In an insulator, the energy gap between the valence band and the conduction band is huge, like a canyon. So electrons can't jump it unless you blast them with some ridiculous amount of energy. And that's why things like rubber and glass don't conduct electricity very well. They keep the electrons locked in pretty tight. And then let's look at the semiconductor next. So uh, this is like the Goldilocks zone, if you're familiar with Goldilocks and the Three Bears, right? So the band gap is small, but it's significant. Electrons can cross it with just a little bit of energy, like heat or voltage, and that's what makes these materials like silicon so powerful. They only conduct when we want them to. And then we have conductors, right? They're always on. So um, there's no gap at all here. In fact, the conduction and valence bands, they actually overlap when we're talking about conductors. So that means electrons can jump freely with zero resistance or near zero resistance. And that's why copper and gold are so good at conducting current, right? There's no leap needed. And here's kind of like the big idea. Large gap, there's no conduction, and that makes for a good insulator. A small gap, this can be a controlled conduction, like a semiconductor. And there's no gap, right? That just means free-flowing electrons, like a conductor. Okay, here on this slide, we're going to go head to head with the semiconductor versus conductor, and we're not just talking materials. We're going to zoom into the atomic level here. So let's go ahead and meet these atoms. On the left, we've got the silicon atom, the backbone of semiconductors, and on the right, it's the heavyweight champ of conductivity, copper. And let's break down this. Let's break this down further. We're going to see that within silicon, you have a balanced player, right? Silicon has 14 protons. Again, 14 protons in the nucleus, and it has 4 valence electrons. These outer electrons, they're fairly tightly held. They're not just wandering off, though. It takes some energy, again, like heat or voltage, to get them moving, and that's why silicon doesn't naturally conduct, but can when you want it to. And we call that controllable behavior semiconducting, right? Let's go ahead and look at the copper now, the free spirit. So copper has 29 protons and only one valence electron. That single outer electron, it's barely held in place. It's all alone, and it can move easily with almost no energy. So basically, it's just free to roam around. That's why copper is such an excellent conductor. Its electrons they're already willing to move. And so the key takeaway here is the number of valence electrons and how tightly they're held makes all the difference. So one loosely held electron can make something superconductive like copper, and something like 4 moderately held electrons, that can lead to some material like semiconductives, like silicon. Okay, so now let's go ahead and compare two superstars of semiconductors, which is silicon and germanium, right? Two elements, one mission. So both silicon denoted with capital S little I, and germanium denoted with capital G little e. Those are the symbols there on the periodic table. They both have 4 valence electrons. That's that magic number that makes them perfect for semiconducting behavior. That means they're naturally balanced. They're not great conductors and not great insulators, but they can be tuned to conduct under the right conditions. So let's look at silicon, right? The industry favorite. It's atomic number 14. It's abundant, it's stable, it handles high temperatures very well. Its energy band gap is just wide enough to resist unwanted current at room temperature. And that's why silicon is the go-to material for transistors, diodes, integrated circuits. Then let's look at germanium. Now, germanium was an earlier contender. It was out way before silicon as a semiconductor material. And its atomic number is 32. It also has 4 valence electrons. But its outer electrons are held less tightly, so it's more sensitive to heat. Right? Since it's a much larger atom, those electrons are further away from the nucleus. So again, that just means that they're less tightly bound. And so less energy is required to kind of move those electrons. So it makes it more sensitive to heat. That makes it more conductive though, but also less thermally stable. And the real difference between these two is that germanium again was actually used first in early electronics. Then silicon took over because it was cheaper, it was more abundant, and it was more reliable as far as high temperature environments. So that's all. The quick thing to take away is that if silicon is a reliable, hardworking, friend who always shows up on time, germanium is the fun, flashy one who's always at the party, but maybe a little too sensitive to stress. Right? Hopefully, that analogy will help you remember these characteristics. Okay, let's go ahead and talk friendships now. Not any kind of friendships, but atomic friendships. Let's dive into how covalent bonds hold the world of semiconductors um, together. Right? So, what is a covalent bond? So, in the heart of every silicon chip lies a beautiful agreement between atoms, and each silicon atom has 4 valence electrons, as we mentioned before, but it wants 8 to feel stable, right? So, what it does, it doesn't steal or lose any, it decides to share. And so it plays a sharing game. So silicon atoms, they'll link up with their neighbors. They'll share one electron each, forming strong covalent bonds. And so with four neighbors, each atom ends up getting surrounded by eight electrons. And it's like everyone putting a hand in for a high five. Right? Nobody loses an electron, but everyone gets a full shell. And why does this matter? Well, uh, because this stable structure is tight and I don't mean tight like in slang, it's tight. I mean, this is a tight, stable structure. And while pure silicon will form these crystal lattices, which are going to be very strong, orderly, and stable. But it's also why just on its own it doesn't conduct electricity very well because it's so stable and it won't actually let go of those electrons. So all the electrons are busy, they're paired up in bonds. And we want to do is we want to break up the marriage here or break up the relationship. So again, until you add energy, like adding a little heat or a little voltage, you can you can break one of those bonds, you free an electron, allow it to move, and it'll leave the hole behind. And the hole is just like where it was occupying, the space it was occupying. And that's when the magic of semiconductor conduction begins. All right. See you on the next slide. So how does current actually flow in a semiconductor? So to answer that, we have to look at something a little bit deeper, and that was energy bands, where electrons live. Electrons in an atom don't just float anywhere. They can only live in specific energy bands. These are regions where they're allowed to exist. So think of it like floors in a building. The first floor is the closest to the nucleus, and then higher floors have more energy, and electrons can't live in the space between the floors. That's the band gap. So going from valence band to conduction band in pure silicon, most electrons are chilling again in the valence band, specifically shell number three, and they're stable, they're bonded, and they're not going to go anywhere. But give them just a little boost of energy, a little. Well, I can't even think of the name of an energy drink. Give it a little bit of Monster energy drink, uh, or give it some heat or some voltage, and then some of those electrons can jump into the conduction band. And what makes the jump, right? So the jump from valence to conduction is what allows current to flow. So once an electron is in that conduction band, it's free to move through the material. And that's how we create controlled electric current in a semiconductor. The role of the band gap, again, if the band gap is too big, electrons can't jump, and that makes it a material good insulator. If there's no gap, right, so they overlap or they touch, they move freely all the time, and that makes for a good conductor. But in semiconductors, the band gap is just right, right? It's not too big, not too small. It's just small enough to allow us to control the uh, gap with just a little bit of extra energy applied. So it shows electrons here on the diagram. It shows electrons stacked in each shell, right? Each shell matching a particular energy band, and the valence electrons are just one energy step below the conduction band, and they're just waiting for that little bit of energy push. Now that we've talked about energy bands, electrons, and what happens when you give atoms a little push, let's go ahead and ask ourselves what happens when an electron leaves, right? So when an electron leaves, you get a hole, right? And suddenly you've gotten this whole electron hole drama, right? Worth tuning into. What happens first is that heat energy will make this happen. So like even at room temperature, pure silicon has enough energy for some valence electrons to get excited, right? Those electrons absorb energy, um, and it's enough to jump the energy gap from the valence band into the conduction band. And then we have a free electron. So let's go ahead and meet our free electron. Once that jump is made, the electron is now in the conduction band, excuse me, conduction band. Wow. And so once it's in the conduction band, it's ready to move. It carries current and it can do electrical work. Now let's go ahead and look back at what's happening where that hole was, where the electron used to be. There's now this vacancy in the valence band, and that empty spot is called a hole. And guess what? That hole behaves like a positive charge. It's not really a particle, but in electronics, we treat it like one because other electrons can jump in and fill it in. And that movement also carries current, right? So when electrons fill in those holes. Then we have this recombination, the return trip. So the free electron might lose energy, maybe by releasing heat or light. It falls back down into a hole in the valence band, and that's called recombination. Then we have electron hole pairs, right? The dynamic dual. So this pair, this free electron and hole, this is the engine behind current in intrinsic semiconductors. It's a constant dance of jumping up, falling back down, and carrying charge in both directions. So far, we've learned that semiconductors don't just conduct electricity, they do it in style, right? Today's topic, two types of current flowing through the same material, and one's called electron current, and the other one's called hole current, right? Uh, Look at your textbook. Does it say electron flow or hole flow? Will determine which theory your book is running from. So let's talk about voltage plus heat equaling free electrons. When you apply voltage to a piece of intrinsic silicon, the heat energy already in the material has freed up some electrons, and then those electrons now live in the conduction band and they're ready to move. We get electron current. So as soon as you apply voltage, free electrons, they begin to drift toward the positive side of the circuit. This movement creates what's known as electron current, and it flows in the conduction band. But what about those holes that we're talking about that gets left after an electron escapes? Well, here's a twist. As electrons leave their original positions in the valence band, they leave behind holes, these tiny positive charges. Other electrons in the valence band jump in to fill those holes, creating new holes behind them. And this chain reaction is called hole current. So it actually flows in the opposite direction of current flow. So imagine an electron jumping in one direction and it's leaving a hole in the reverse direction. So imagine holes going in one direction and electrons moving in the opposite direction. So again, this is where we get the two currents through one material. Even though the electrons are the real moving particles, or the only things that are actually really moving, we treat holes as if they also are moving. So because their motion explains how current flows through the valence band, we talk about two currents happening at once, electrons moving freely in the conduction band, holes being filled in the valence band. You might want to think of this like maybe people moving from a house to the next door neighbor's house because maybe they like the house by the lake or something. And what's happening is as an opening opens up closer to the lake, an owner will move to the very next house, very next house. Let's just say they're on a waiting list. And what happens is a hole is actually opening up in the opposite direction that the family is moving in, if that makes sense. Anyway, let's finish this slide up. So this is what makes semiconductors versatile. They don't just rely on one type of charge carrier. They use both, right? The positive and the negative, or the electron and the hole, or in our family analogy, the family moving into the next house and an empty house, right? And so by controlling which one of these dominates, we can create diodes, transistors, and even solar cells. Okay, we explored how both electrons and holes contribute to current. So we're going to go ahead and zoom in on what that really looks like inside a piece of silicon if you look up at our slide here. So you're looking at a chain of silicon atoms, each sharing electrons in strong covalent bonds. And now let's say a free electron breaks out, leaving behind a hole in the valence shell, and that would be step one. The chain reaction begins. So now another electron nearby jumps in to fill that first hole, but in doing so, it leaves its own hole behind. And so again, this process continues. One electron fills a hole, leaves another behind, and the chain repeats, and the hole appears to move in the opposite direction. And this is what's cool about the whole thing. Even though only electrons are actually moving, the holes behave like mobile positive charges, and they move, in this case, left to right because the electrons are hopping right to left. Um, if it helps that you're imagining uh, a street of homes and people are moving from the right to left, and let's just say the lake or whatever they want to be at closer to the lake, maybe it's a school where they drop their kids off. Um, they're moving in one direction and they're leaving a house open to their other side. But then the next neighbor moves in, and so it's going to look like that empty house is moving all the way down. Um, Try to visualize that. It's pretty cool. All right, so what do we say? So from a current flows perspective, electrons are moving in the conduction band, holes are moving in the valence band, and both are essential in semiconductor operation, especially when you have p-type material where holes are the main major carrier. So again, this diagram shows each numbered step when electrons hop and to a new hole being left behind after every hop. The gray arrows show the effective movement of the hole, like a spotlight shifting on a stage while dancers move from uh, direction to direction, one side to the other side. All right, hopefully that helps. Okay, after learning how pure silicone moves current using electrons and holes, it's time to supercharge it with a little trick called doping. So why pure silicone isn't enough? Well, silicone in its pure form, again called intrinsic silicone, doesn't conduct current very well. And it doesn't because there aren't many free electrons or holes available. Remember, it's kind of balanced. And that makes it useful as a base, but not a great building material for reliable electronic devices. So this is where we enter the idea of doping. And doping, it just means adding tiny amounts of impurities, and just like a few atoms per million. So we do this in this case to silicone. We add it to the silicone crystal, and this turns intrinsic silicone into extrinsic silicone. And we do this again through the process called doping. So again, doping, just adding a little bit of impurities. And there's two ways we can dope. We can dope with N-type material and P-type material, right? There are two main doping options, and each one of these creates a different type of charge carrier. So if we dig first into the N-type, which is the negative type, we add atoms with 5 valence electrons, like phosphorus or arsenic, and then 4 electrons bond with the silicon lattice, and the fifth electron is left free to move. This increases the electron current for when we add N-type doping or N-type impurities. So in this case, electrons again are the majority carriers in N-type silicon. And P-type silicon or positive type, we add atoms with only 3 valence electrons like boron or gallium. And these atoms form only 3 bonds, leaving one hole. That hole behaves like a positive charge. And so holes are the majority carriers in p-type silicon. And this is important because with n-type and p-type semiconductors, we now have customizable conductivity. And by combining these two, we can create p-n junctions, or what are called p-n junctions. And we'll look at that in a little more detail in the next couple of slides. These are the building blocks of diodes, transistors, and nearly every microchip that you've ever used. All right, we've discussed doping, the secret that turns basic silicon into a functional electrical material. Let's go ahead and focus on the first type, which was N-type semiconductor. And what is N-type again? N-type stands for negative type because the majority charge carriers are electrons. And here's how it works, right? So start with silicon. Pure silicon atoms each have 4 valence electrons. They perform, they create these perfect covalent bonds in the crystal structure, but we want more free electrons, so we shade things up. We add pentavalent atoms. So enter the dopants, which is the doping impurities, and these are going to be atoms with 5 valence electrons. And again, it could be phosphorus, it could be arsenic, it could be antimony or bismuth. And these atoms are called donors for this reason, because they bond with silicon. Only 4 of their electrons are needed to make stable bonds. And that fifth electron, it's extra. It just becomes a free electron after this reaction. So meaning we have more electrons, we can have more current. The fifth electron, it doesn't stay locked in place. It's just ready to move. And it gives us more conduction band electrons. And suddenly silicon can carry current much more easily. So again, a big recap for this slide. Majority carriers are electrons. Minority carriers are the holes. The dopant atoms, these are pentavalent, meaning they have 5 valence electrons. And the result is that this boosts conductivity using extra negative charges. Okay, let's go ahead and flip the charge, literally. So we've covered N-type semiconductors and free electrons. Now let's talk about the other side of that coin, which is the P-type semiconductor, where holes take the lead. So why do we need P-type? So in pure silicon, again, electrons and holes are equal but limited. If we want to build devices like diodes or transistors, we need more control, and that's where p doping comes in. We add trivalent atoms or three valence electrons, atoms with three valence electrons. And we dope silicon with atoms like boron, indium, or gallium, and each with just three valence electrons, and these are called acceptor atoms. So what's happening here? Silicon needs four electrons to form bonds with its neighbors. A trivalent atom like boron brings only three. That leaves a missed bond, which is going to be a hole, and that hole is the key. So this hole acts like a positive charge carrier. It can accept an electron from a neighboring atom, creating a new hole in the previous spot. And this continuous chain of hole filling and hole leaving allows current to flow, even though it's just really electrons moving around. So let's go ahead and recap this slide. We have p-type material, which is positive type. The dopant atom is a trivalent, meaning three valence electrons. And the majority carriers for p-type is holes. The minority carrier is the electrons. Again, just the reverse from the last one. And the role here is they accept electrons and enable current through hole motions, so through hole flow. All right, welcome to Circuit Chat, where we talked about atoms, energy bands, electrons, and doping. Now it's time to bring it all together with the PN junction. That's the place where magic meets silicon. So what is a PN junction? So when you take one side of silicon and dope it with trivalent atoms, you create that p-type region that's full of holes. Then you dope the other side with pentavalent atoms, making that side the n-type region, which is full of extra electrons. Now where they meet, the boundary between these two regions is called the PN junction. This junction isn't just a line drawn in the sand. It's that was no pun intended there. It's a functional barrier where all the real action happens in diodes, transistors, solar cells. And what happens at the instant of formation is what determines this. So when the junction forms, we have electrons from the N side that start to diffuse into the P side, right? Because they're negatively charged, the P side is positively charged, they attract. And then at the same time, holes from the P side move into the N side. And they meet and recombine. They cancel each other out near that boundary. And this creates a region with no free carriers. So in other words, there's no free holes and there's no free electrons down that center. And we call this the depletion region. So the depletion region equals this built-in barrier. Um, and so within this region, it acts like a wall or maybe a hill that you have to overcome to have movement, charge movement. And so without any external voltage, it prevents current from flowing. But with the right biasing, meaning the right voltage to overcome that, you can control whether current flows or not. And that's what makes a PN junction the basis of switching and signal control in semiconductors. It's the heart of modern electronics. So everything from tiny diodes that let current flow in one direction to powerful transistors in your phone CPU to solar panels converting light to energy. Every one of those has a PN junction. And that's it for the fundamentals in circuit chats. If you followed along, we've talked about atomic orbitals all the way up to the gates, which form what later you'll realize is digital logic. And again, whether you're using this to design devices or just curious how your phone works, this is where it all begins. So we've discussed the formation of the PN junction. Now we're going to go ahead and pick it up from there and see what happens after that first connection is made. So we end up with a junction, a bridge, or a barrier. So when p-type and n-type regions meet, right, free electrons from the inside started to diffuse across the junction, again, because there's holes waiting on the P side, places to fill. Again, electrons and holes recombine as electrons cross into the P region. They recombine with holes that neutralizes them, and this process creates negative ions on the P side and leaves behind positive ions back on the inside where the electrons came from. So this is where we get that depletion region, the area where this recombination happens. It's depleted of free carriers, no moving electrons, no moving holes, just fixed positive and negative ions that are stuck in place. And we produce this barrier potential. And this creates something new. It's a built-in electric field across the junction. We call it a barrier potential. It acts like an invisible force pushing back, saying, No more free charges shall pass. You shall not pass. I don't know. Uh, yeah, thou shall not pass. Whatever that was, unless you add some kind of energy. And what does this mean for current flow? So without external voltage, the barrier holds strong. If you apply a forward voltage, the barrier lowers and then current starts to flow. If you apply reverse voltage, the barrier just grows and current is blocked even further. So this is what makes it an on-off switch, like an on-off switch, gives that on-off switch behavior. So again, electrons diffuse, holes are filled, ions form, you get a depletion region that appears, that produces an electric field, creates a barrier potential, and then that's how the PN junction gains control over the current. Now that you know about the PN junction and the mysterious depletion region, we're going to keep diving deeper into what actually builds that region and why it's the gatekeeper of all diode behavior. Right? One more time to recap: two regions, two roles. P-type region, we've got holes, right? Thanks to the what? Trivalent dopants like boron, right? And then we have the N-type region where we've got extra electrons thanks to what? Right? The adding of that impurity of the pentavalent donors like phosphorus. The big diffusion moment. So when the p-n junction forms, electrons from the inside start to diffuse inside. I didn't say inside, right? That starts to diffuse into the p side. Again, because holes are missing electrons. Filling of the hole neutralizes the charge. Depletion region is created, and trying to repeat what I said last time without going back to the last slide. Um, right, depletion region is created. That creates a charge barrier. That just means that as more electrons cross and combine fixed charges, they build up on both sides. So negative ions on the p side, positive ions on the n side. That creates that electric field, the barrier that opposes further movement of free charges. And again, we have the depletion region where no free carriers remain. Um, that's a good recap. Diffusion creates the buildup, ions create the electric field, the field resists further movement, and this is the depletion region, the core of the diode function. Today we are unlocking the barrier in the heart of a diode, the barrier potential inside the depletion region. I've repeated myself multiple times on purpose, a little bit of redundancy, that way you can hear the terms and hopefully have this understood by the time we get to this slide on the very first listen. If you haven't been paying attention, you're going to have to go back a few minutes. All right, so what's in the depletion region? Again, once that p-n junction forms, a region is left behind that's stripped of free charge carriers. What's left are fixed ions. Again, the negative ions are on the p side and the positive ions are right on the other side of the n side. This sets up an electric field. It opposes charges um, from further combining, right? So opposite charges pull toward each other. It forms an electric field, resists further movement of electrons and holes. Again, it's acting like a gate there. Uh, so there's a barrier potential to, if you want to push an electron across the barrier, you need to apply energy, external energy, just enough to overcome that field, and we call that the barrier potential. We measure it in volts. For silicon, we know what it is. It's 0.7 volts, or we designed the diode to be at 0.7 volts. And for germanium, which is the older one, was 0.3 volts. If you put anything less than that, no current's going to flow. If you put just enough or a little bit more, electrons break through and then current starts flowing. So you're going to find out it's not exactly 0.7 volts. It might be, like for silicon, it might be 0.69 something when you're measuring. That's fine. But again, for calculations, ideally just use 0.7 for silicon and 0.3 for germanium when you're designing. Direction and polarity, they do matter. So to get through the barrier, you need the right voltage in the right direction, and we call that forward biasing. Right? If you get it wrong, if you increase the barrier instead by putting the voltage backwards, yeah, you're just going to further block it. And you're going to increase the barrier. But if you forward, which is called reverse biasing, if you forward bias it, you're going to allow current to flow. So the key takeaways here are that opposite ions create the electric field across that p-n junction. That field equals resistance, which equals which can be overcome by a barrier potential. You have to apply that voltage across that potential, and that's what allows the diode to control current flow. Okay, today we're wrapping up our look at the PN junction by seeing what it looks like through the lens of energy. And that's right, we're going to break it down by the energy diagram of a diode. Energy bands and what you're looking at. So the vertical axis in these diagrams represents energy. The conduction band is up top where electrons can move freely, and the valence band is down below where electrons are still tightly held. So the farther an electron has to travel vertically, the more energy it's going to need. On the left side, the formation phase, we see what happens as a p-n junction forms. Majority carriers, holes in p-type, and electrons in n-type, they start to diffuse. Electrons drop into the holes, releasing energy and forming fixed ions. And this activity builds up that barrier potential, which separates the two regions. On the right side, to establish equilibrium, we hit a stable state. So electrons and holes can't easily cross anymore. And there's a built-in slope and energy at that junction. So this is called the depletion region. It takes about 0.7 volts for silicon or 0.3 volts for germanium to move a charge carrier across that barrier. So think of the barrier potential as the slope to climb. It's like pushing a cart uphill until you supply enough energy to get to the top, and the cart isn't going anywhere um, until you get past that barrier potential. Right? You're not going to cross over that hill. Um, and think of that hill as the energy you have to cross. So this diagram is pretty important. It gives you a visual. It explains how current can only flow when you provide enough energy to let electrons hop from one side to the other. And it's the key to understanding how a diode turns on and turns off. And that's it for the core theory of semiconductors, right? You now understand atoms, electrons, holes, doping, p-n junctions, and barrier potential, which is the foundation of all modern electronics. So go ahead and join us next time on Circuit Chats as we go from theory to real-world biasing, breakdowns, LEDs, and a bunch of other cool stuff.